So Tiffany Capillari is coming to us from Southwest Research Institute, and she's going to talk about MoveIt for aerospace automation tasks. Can you
let me share my screen right now.
Yeah.
All right. Yeah. You can see it, right?
Yes, that works.
Cool. Okay. Yeah. Hi, everyone. My name is Tiffany Capillari. I'm at Southwest Research Institute, and I'm going to be talking about constraint motion planning using MoveIt in one of our projects on aerospace automation. So first, I just want to tell you a bit about Southwest. So we are based in San Antonio, Texas. We're an independent nonprofit organization focused on research and development. We do everything from deep sea exploration to aerospace automation and like space exploration. We do focus more on natural science and engineering, but we do a lot of things. And so today I'm talking about one of our projects for automation for aerospace. And the reason we work on these projects is to improve human safety as well as the quality for manufacturing processes for building these planes, and it would also improve productivity as well as reduce costs. However, of course, there are many challenges to these projects. For example, how large the components and assembled aircrafts tend to be, and moving them around to specific machines and everything would be quite the ordeal. And building specific machines to do just one specific task can also get very expensive very quickly, as well as having limited CAD and as-built model data just adds to the challenges. So the project I'm talking about today specifically is the A5 program. And so A5 stands for Advanced Automation for Agile Aerospace Applications. It's funded by the Air Force Research Laboratory, and Southwest is working with the National Center for Defense Manufacturing and Machining, Boeing, as well as Robbins AFB in order to work on this. And the key goals for this project is to be able to take the automation to the part so that we don't have to move these large pieces around. You would need no prior knowledge about the part or the environment in order to use A5, and the operator would need to be some expert programmer or even any sort of expert. It should be able to be used by any average person without prior knowledge of it, and it would also be easily reconfigurable for new manufacturing processes, so it's not hyper specific on just one task by itself. But today I am focusing on just a single task that they can do, which is X-ray inspection. So we want to be able to autonomously detect foreign object debris in F-15 inlet ducts after completion of maintenance tasks. And here on the side, you can see a mock-up of an image of our robot. And at the bottom here, you can see the tool that we use for the X-rays. So we need to be able to put these inside of the inlet ducts in order to take the X-ray images. And so the problem here becomes constrained motion planning, as you've seen the tool is quite large and unwieldy, and we need to be able to insert it into the duct, which is a pretty constrained space. And it also needs to be in a fixed orientation in order to be able to take these X-ray images. So I'll be calling, basically the glass upright constraint. And we also want to be able to move to discrete viewpoints that are defined in Cartesian space relative to the inlet duct. And so today I'm going to be going through a couple of different implementations that we've tried throughout the scope of this project. I'll be beginning with the simplest implementation first and ending on the one that we've landed on. And these are mostly using the RRT Connect planner. So for our first approach, we just try to have a motion plan request to a Cartesian goal with the tool upright orientation path constraint. And you can see in this video here that it does seem to plan it relatively well, and it planned it pretty quickly. However, since the goal is in Cartesian space, the planning and sampling also happened in Cartesian space. And so you can see in the video right now, it completely violated our constraints and hit the airplane, which obviously isn't a good thing for it to do in real life. And while this did have a very high success rate in a relatively short amount of time, and the sampling in Cartesian space did result in reasonable trajectories, it unfortunately didn't detect collisions causing the joint space in which the robot is actually moving. So these were detected during planning. And so when the robot would actually move, it would end up with these strange violations. And so we moved on to our second. I'm sorry, my PowerPoint is crashing. Sorry, my PowerPoint just crashed. Let me try restarting it.
So while it's restarting, could you maybe say more about why those collisions are not detected? That seems strange.
Yeah. Sorry, it's just restarted. Let me just share it again.
Right. No worries.
Yeah, sorry about that.
Sure.
Yeah, so it doesn't seem to detect it because it's finding it in the Cartesian space and sampling only in Cartesian space, and then it snaps to a solution state that it finds. However, when it's actually moving in the joint space, it will do some strange little like joint flips and reconfigurations to move that aren't shown in the planning because the planning just snaps to the correct solution. So obviously that was not ideal for us. So we moved on to a second approach in which we tried using force planning in joint space in order to avoid missing these joint configuration changes that would happen during planning. And unfortunately, while this did work better, planning was always took much longer. So it was never planned in an acceptable amount of time for us. It would always take more than a minute. And almost all of the OMPL samples were rejected. And you can see there, it just did another strange little joint configuration flip. And a lot of these samples were rejected because they didn't meet the glass upright path constraint. And so we found that satisfying a Cartesian orientation constraint by sampling in joint space is very difficult. So for our third attempt at this, we are basically trying to do a very similar thing to the last approach. However, this time we sampled a very large number of joint states before beginning planning. And using this, we created a database of states that we knew were collision-free and also satisfied our path constraint, and used those and had OMPL use those predetermined states to find the best path. And this did have a much higher success rate within an acceptable amount of time. However, they had a few issues, as most of these motions were classic OMPL trajectories. They were unintuitive and had a few extreme motions. But you can see here that it did, for the most part, work. It gets very close to hitting the inlet duct, though, on the side. And we found that since MoveIt uses the IK solver to generate goal states given a Cartesian state space goal, and OMPL grows that search graph out of these solution states, the user would have little control over which goal state becomes part of the solution trajectory. And we also found that OMPL planner tuning isn't quite sufficient for making these plans any better. So again, you can see as it comes out, it's very close or even does hit the inlet duct. And we decided that having sane and intuitive motions is critical for system acceptance and building trust with operators, as having these sort of more extreme motions would scare a human operator that hadn't seen it before and isn't sure whether it's going to hit the plane or not. And if it gets that close, it's possible for it to actually hit the plane by accident. And so we decided to try another approach. So for our fourth approach, we went with a more hybrid version of our previous plans. So now we use a Descartes planner, which is a Cartesian motion planner, in order to first find these optimal joint states for each scan position that we know the robot needs to go to take this X-ray. And then we use the IK solver to find all these valid joint poses for each scan waypoint and use them to create this acyclic graph, connecting each possible joint state between adjacent scan waypoints. And through that graph, we want to be able to minimize the amount of joint motion that happens, because we want the robot to move as little as possible while still completing its task. And so we find the shortest path through that directed acyclic graph. And then finally, we then use OMPL with this path that we found, with our path constraint, in order to plan between these optimal joint states And that way we can find a much better, more intuitive path. And here, as a result, you can see that the planning success rate is pretty high in an acceptable amount of time. It only takes about 30 to 45 seconds to make these plans. And Descartes was able to find joint poses that minimize the amount that the robot needed to move up and down the rail, as well as its manipulator. And as a result, the OMPL plan motions were much less extreme than in the previous approaches that we tried. And you could also see in this video here that it didn't get too close to hitting the plane. It didn't do any extreme motions or big joint flip configurate or reconfigurations as we've seen in the previous videos. So like in conclusion, we found that state sampling in Cartesian space can be much more effective than state sampling in joint space for certain applications of planning constraints, as when we tried to state sample in Cartesian space at first, it wasn't able to see these joint configurations that would happen during the actual planning phase. And collision checking should probably occur in the state space in which the robot moves, not necessarily its planning space. Because again, we originally were planning in Cartesian, but the robot was moving in joint space. And a few other potential effective solutions that we thought of but haven't implemented was using TrageOpt instead to directly optimize with these desired constraints. We also thought about customizing the OMPL interface for ourselves in order to sample in Cartesian space, but do state validation in joint space instead of Cartesian, so that we would see these like joint configurations. We also thought of another hybrid solution that would build off of our last solution, which was the one that we are currently using, and which we would also use TrageOpt to further optimize this trajectory that we've created. And some suggestions for the MoveIt OMPL that we've thought of during the course of this project is collision checking in the robot motion state space rather than planning space. Having a motion plan viewer that would interpolate between the states in the robot motion space rather than just snapping to the solution state. As in the first pass, you could see that while the robot motion looked like it would work fine, and when we actually executed the path, it had these joint flips that completely disregarded the path constraints and would hit the plane that weren't visible before we executed it. And also, if we were able to weight the joints for OMPL differently, we'd be able to tell it which joints we want to be able to move more or less, so that we could further optimize our trajectory and have the robot move as little as possible. Thank you.
Thanks so much for that presentation. Can you go back to your previous slide? Because I think that's you essentially ended with like a set of questions or challenges for our MoveIt community. It's like, hey, you know, this is something that would make MoveIt much better.
Yeah.
I can't speak to all of it. I will say I think that last bullet is something that is supported in MoveIt, although it's kind of very buried in the bowels of MoveIt. There you can associate weights with joint angles, I think, so you can actually effectively say, you know, displacement of the pinky finger should weigh less than the displacement in the shoulder angle. So that it is possible. But yeah, that could be better supported.
Okay. Yeah, sorry, we didn't know that was already supported.
No,
we didn't find any documentation on it.
Yeah, it's not just, oh yeah, edit this YAML file and you're done. It's not that simple. So it's probably something that could be better documented. But yeah, I don't want to hog all the question time. I'll like to give other people an opportunity to ask questions or answer your questions. Is anybody who feels that they want to speak to this? Michael, I think you can still speak. You're still a guest host if you want to answer your question in person.
I guess the takeaway is we can definitely improve. So yeah, when I listened to your, I also remembered a few of my students and also myself working with these interfaces. And yeah, I think you had a very typical journey through all of that. And you came up with solutions for your problems. Great. Yeah, as Mark also pointed out, I think for many specific things, there are better solutions if you know more about it. But then, of course, the knowing more about it is where good tutorials come in. So thank you for
Yeah.
providing that feedback.
Yeah.
And MPC wouldn't be a nice framework for that task.
Yeah, similar comments about the constrained motion planning. Like in theory, a lot of these problems can be solved. In practice, it's very hard to actually make that happen. Like in theory, I think a lot of constrained motion planning that our previous speaker had presented, like, yeah, he's done all this amazing stuff, and exposing it and MoveIt in a generic way is actually very, very hard. And we had this whole Google Summer of Code project around it, and we got some of the way there, but it was still quite a bit of work to even just marginally supported in MoveIt too, and it's it's still a work in progress. It's still not as generic as we would like it to be. In an ideal world, you could say here's an implicit function that says that returns 0 when your constraint is satisfied, and like something non-zero everywhere else, and you can just use that. And the MoveIt should just plan using that constraint. And yes, that's possible in theory. In practice, right now, not so much. So, yeah.